let's at least go through this quickly and at least some notations, and maybe at least the part on set expressions and how it relates to propositional logic is maybe not familiar for all of us. And actually some of the proofs I introduced there, I don't find them in ordinary textbooks at least. So first, in discrete mathematics, we have, and specifically propositional logic, we have what we called basic atomic propositions. And here I just denote them P, Q, R, and S. I mean, a statement could be the sun is shining, etc. And in our case, we have atomic propositions, for instance, that you have a specific property of a state, for instance, that a state is forbidden, a state is marked, or a goal state, etc. So those are typical applications in our case. Compound propositions is just that you combine with the standard logical operators like and, or, implication, etc. A tautology is a statement that is always true, and that is logically described in this way, that, okay, either P or not P, and that means that it's something that is always true. And then you use this special notion before to write this. You could also have something before this, and that is more than a kind of implication where you say, okay, if this is true, then it also implies this. But quite often here we just use this notation to say that, okay, if this is something that is always true, then it's a tautology expressed in this way. Contradiction means that it's always false then instead. And then if you have P and not P, that can of course never be true. Because if P is true and you combine that with not P, then it's always false. So it's a contradiction. Then also the so to say labels here, T and F, are used to express tautology and contradictions. So an equivalence is then a biconditional statement that is always true. So you could say that an equivalence written with this double arrow, it's written either in this way, it could also be an equal with three horizontal lines, but I mostly use this notation. But that could also be said as this biconditional statement is always true, and which means that if and only if. In the literature, quite often, this type of arrow is also used for the biconditional statement, which, remember, is a logical statement that can be true or false. So let me illustrate this. I think I need to go out again and try again and see if it works now. At least it worked this morning. Yes. Okay. So let's look at this truth table also to see what kind of combinations we have here. And of course, if P is true and Q is true, then P and Q is true, and not P is false. And the implication here, or the conditional statement P conditional Q, it's also true, as well as the biconditional statement. But here comes something strange, and that is that this conditional statement, which we quite often also say is an implication, it is not true if P is true but Q is not true. And that is natural, because this so to say conditional statement says that, okay, if P is true, then Q must also be true. And if P is true and Q is not true, then this statement is not true. While the opposite, if P is false, it does not matter what Q is. it's always true. And this is sometimes a bit surprising, but it's just to note that that is the fact. The biconditional statement means that you have the conditional statement in both directions. And then it means that, okay, if both P and Q are true, then the biconditional statement is true. And if both are false, it's also true. But if one of them is true and the other is false, in both directions here, the biconditional statement is false. So here you see once again that this biconditional statement can be true or false, but if I write it, if I say that it's an equivalence, it's something that is always true. And just to understand what that means, we have here a list of a number of equivalences. For instance, that it doesn't matter in which order you say P or Q, or the opposite Q or P, they are equivalent. And for instance, if you take the double negation on the statement, you get it's equivalent to the statement itself. Here comes also some famous rules, for instance, De Morgan's rule, saying that the negation of an or condition is the and of the individual negations. And of course, then you have the opposite, that if you have a negation of an and, you can express that as an or between the negation of the individual ones. That's quite a useful equivalence. And here you have that if you have a number of or conditions, it doesn't matter in which order you take them, while it's very crucial if you have a mix between and or, in which order you take the parentheses, so to say. So P and parentheses Q and or, that's equivalent to P, and here you can consider and as a multiplication operator and or as an additional operator. So P and Q, P multiplied by Q, or P and or. So these are important to consider. Here is another thing, that if you have P or or a contradiction, then it doesn't matter what if P is true, it doesn't matter if the rest is true or false. Or what do I say? Here now, maybe I say something. No, okay, P or contradiction is P, while, okay, P or true, that means that it's always true. Sure, because it's enough that one of them is true, then the other one doesn't matter. Here we also have some other, this is a very important rule. So the conditional statement P conditional Q is actually not P or Q. So this is a translation back to the basic logic expressions. So that means that actually all the conditional and even biconditional statements can always be expressed only using and or and negation. Actually, all of these statements can be expressed by using only or and negation, or instead negation and the and operator. So those are the most fundamental operators. Actually, it is possible to go back to only one operator, and that is the NAND, negation of and. That can express everything. But these are more peculiar details. Of course, truth tables can be used to prove, for instance, different aspects, like say this one, that P conditional Q and Q conditional P is equivalent to the biconditional statement P biconditional Q. And that means that for all combinations of P and Q, the result in the truth table are the same. True for the first, false for the second and third, and true for the fourth. So this is a way to, here, for instance, we have this interesting aspect that not P or Q is equivalent to P conditional Q, means that they have the same truth values. Let's see, I think that was enough. In the same way, we can go back here and also note that an implication is a conditional statement that is a tautology. So P conditional Q and the fact that this is always true, that is denoted in this way. But once again, remember that in some computational literature, this statement, which is a relation between P and Q, is sometimes considered as a statement can be either true or false. That means that it's just a statement. So this is a bit confusing, but in pure mathematics, I would say that this is clear, that there is a clear difference between the single and double arrow. Based on these equivalence relations, we can actually prove some more complex expressions. And I will soon show you this. But before I give you a couple of examples, I will go through the whole, well, let's call it theory if you like. And because then I will switch to another presentation. Implications, here is also a list of typical implications. For instance, that P and Q implies P, while P implies P or Q. And you can continue this with a number of interesting expressions, which typically are given in mathematical tables. Actually, I will prove some of these implications a bit later on as some exercises. Yeah, this is a tautology, and yeah, I think I can take that. I will have that in the other slide too, but I think you can read this. So let's go on with this. What I will show you here is that this statement is actually something that is always true. And okay, you can do this by truth table, and then I think you get 16 different instances because you have 4 variables here. So it's quite long truth table. But you can also show this by quite more quickly by using these equivalence relations. So let's show how that can be done. Here, there is a rule, equivalence 23, saying that P implies within parentheses P or conditional, P conditional within parentheses Q conditional R is equivalent to P and R conditional R. And actually, this is a rule that I have used myself in some proofs, which is related to more relations and more specific efficient methods for abstraction, and etc. So some of these rules are quite relevant here. If we apply this, and now this R here is actually R conditional, R conditional S. So first we apply the rule I mentioned, this E23, which means that you can take P and Q conditional R conditional S. Then if we look at the rest here, then we can also make some, we can use this, let's call this multiplication or the mix between or and or. And then we take P and not P, or P and Q. That is exactly what we show here. So now I have evaluated that part. And then we have and the negation of R conditional S. Now we know that P and not P is a contradiction. That's always false. But false or something means that the false part we can skip. And so here we only get in the end P and Q and not R implies S. So let's sum up here. We have P. Oh, okay. Here I've also now used this conditional replaced with not on the first or the second. So not P and Q or R conditional S or. And then here we have P and Q and not R conditional S. But now I remove out the negation here. So I use the De Morgan's rule. So then I have a negation of, and then I need to put a negation there. And I change this and to an or, and then I can skip that negation operator. So now I have negation of negation P and Q or R implies S. Okay, why is this a tautology, which I've written here? Because what you see here is the same as you see here. And here you have a big statement or not this big statement. And that is a condition that is always true. Okay, so then comes another statement which I will come back to later. That's an implication. So you see here that this quite long expression I was able to show by only making through two actually equivalence reformulations. I don't say that it's always so easy. Actually, it's very easy to develop all these things, and in the end you come into a mess. So you should be careful to look at the structure of these formulas to see if you can find some pattern. And in this case, it was a clear pattern. Yeah. Then we come to some proof techniques which you see in more or less every textbook on propositional logic. First, that an equivalence can always be proved by making an implication in both directions. So P implies Q and Q implies P. That shows the equivalence. And actually you have that all the time in mathematical proofs. Because if you say that if and only if, then you show that in both directions. So first if, baba, if the first brings the second, and then you look at the opposite direction. So this is actually very common in mathematical proofs. Then another thing which is also quite common is proof by contradiction. And that is simply that P implies Q is actually equivalent to the contradiction of P and not Q. Let's see why that is the case. First, P implies Q is a tautology on the statement, on the conditional statement P conditional Q. So this is the same as this, and that's why I now write also if and only if IFF in between here. Of course, I could have written if and only if is an equivalence, but then I have too many levels of too many arrows back and forth, and so it's sometimes important to put a hierarchic construction of these proofs. Okay, now we look at if we can make something different out of this. Yes, this can be expressed with the replacement of P conditional Q with not P or Q. Then we use the De Morgan's rule on this. So we move out the negation, and then we get P and not Q and the negation outside that. And the tautology of something that is not true is the contradiction of the final statement here. So now I have proved that P implies Q is equivalent to the contradiction of P and not Q. Actually, these examples on implications and contradiction, I will come back to that in some additional slides later on. So now I will quickly go on with discrete mathematics and predicate logic in this case. Why I have the headline here, discrete mathematics, is that in my lectures, I started a new lecture here, so that's why it looks a bit strange. But now we are going for predicate logic. And actually, predicate logic is very useful also when we come to these automata. And predicate logic is also useful when you want to prove some specific set operations. So that's the motivation why we introduce first propositional and then predicate logic. So what is the difference between predicate and propositional logic? Predicate logic is simply a logic where you also allow yourself to introduce variables. These variables can, for instance, take integer numbers. So for instance, the domain of these variables could be, for instance, all positive natural numbers. In this case, I assume that 0 is included in the natural numbers. Sometimes it's not. Generally, we say that the domain of your variables, they could be some elements a1 to an, but often we use integers here. Now I will illustrate how we can reason about these statements where we have extended, we have still propositional statements, but based on variables. And here is a simple automaton where actually we can see here that from state 1, we cannot reach state 0. Because from state 0 you can by an event reach state 1, but there is no arrow from state 1 to state 0. So you can say that state 0 is a non-reachable state. So one predicate I will look at is formulate a predicate saying which states are reachable. But before that, we can just take a look at the structure here. We can see that we have from state 1, we have a transition to state 2, as well as 3, followed by 4, or we can go to state 5 or 6. Now you see that I also introduce some additional properties on these states. So I say that state 4 is a marked state or a goal state. We really want to go to this, achieve this state 4, while we consider state 5 and 6 to be forbidden. I will come back to the motivation for this. But right now, I just want to formulate a predicate saying that which, or model stating which states are reachable. So I formulate that then a predicate I called PR of X. So that is either X is equal 1, our variable. So you could say that now I introduce a variable X, which takes these different values. So if X is your state variable, which can take value 0, 1, 2, etc. So this you can express as X is equal 1 or X is equal 2 until or X is equal 6. But that is, of course, equivalent to that X is in the interval from 1 to 6. So x is larger or equal 1, and x is less or equal 6. So these additional operators, which we now have extended to when we use variables, especially integer variables, we have equality, we have less or equal, and we have greater or equal.
Professor, there is a question by,
yes?
there is a hand raised here.
Okay, let's take a look at that.
R. Goyal, please ask question.
Yeah.
Question is that x is equal to 1 is not a choice here because 1 is the initial state. So, I mean, every journey has to start from the state 1 only. So, probably x is equal to 1 may not become the part of the reachability predicate. And moreover, one reachability path could be from 1 to 2 and 2 to 3 and 3 to 4. Or it could be from 1 to 2 and then 2 to 5 or 5 to 6. So I'm unable to understand these two things.
Okay, good comments. I will try to explain this. First, the definition of reachability could, of course, be made in a more mathematical and strict way. But let me try to explain what I mean by reachability or by the reachable states. And then you start in the initial state, and that means also that the initial state is reachable. That's in our definition, that's in the meaning of reachability.
But then journey has to start from 1 only. There is no choice. I mean, journey cannot start from neither from 2 or from any other state except...
Yeah, but remember, I have an arrow here. I say that state 1, that's a big point, of course. I have an arrow here modeling that 1 is the initial state. Of course, I could have said that, for instance, a non-deterministic case saying that state 3 could also be an initial state. Or let's say that state 3 is the only reachable state. And in that case, the only initial state. So move that arrow to this state instead, which are then the reachable states. Then it's only x is equal 3 or x is equal 4, which is the predicate for the reachable state, because then it's only state 3 and 4 that are reachable.
Yes, but certainly we cannot have more than one initial state because this whole stuff is being modeled as a finite automata and not as a transition graph.
Yeah, but I mean, now I'm just talking about, I just give an example here. I have the freedom to state which is the initial state.
Right.
That is the freedom I can take. That is a decision I can take.
Right, so right.
And the second interesting thing is that I can even introduce more than one initial state. For instance, there are applications where we consider all states to be the initial states. In some security applications, for instance, when we model that from the beginning, we don't know anything about an intruder, for instance, then we say, okay, it can be in any state. And then I say that the set of initial states is all states. Then when you suddenly get a registration of an event C, then you realize in this, the guide started in state 2 and went to state 3, and then suddenly you know everything about your intruder. So
Manveer also has a question, Professor.
Yep.
Manveer?
Yes, ma'am. So can we say that the initial state is by default a reachable state?
Yes, in some sense you can say that.
Because we have started from 1 as initial state, we can say by default it will be considered as a reachable state.
Yeah, I would rather say it in this way, that from all states are reachable if there are forward transitions from the initial state. All states that have a forward transition.
Right.
Here you go forward. And that means that all these states are reachable. Then we will later on look at backward reachability, for instance, from this state, and then we go in the opposite direction of the reachable, of forward. Instead, we go backward from in the opposite direction compared to these arrows. So forward and backward reachability. But when I only say reachability, I mean forward reachability. So I try to repeat again, and I hope this is clear now, that the reachable states you get if you start in the initial state, and in this example, I have said that state 1 is the initial state. And then you go forward, you get into state 2, and here you can go in 2 directions. And this is also actually a good example of what I will, in the end of this presentation, mention about a breadth-first search, because reachability is typically implemented by a search in this graph. And in that case, it's a breadth-first search. It means that you go in all directions. You compared to, for instance, deep-first search. And deep-first would mean that you go in only in one forward in one direction if you have alternatives until you reach a final state or a terminal state. That's the deep first, and for typical reachability, you go instead, as soon as you have an alternative, you take both alternatives. So first you have state 1, and then by the first step in your reachability, you also include state 2, and then your reachable states are 1 and 2. Then you go both for to state 3 and 5, and then suddenly your reachable states are 1, 2, 3, and 5. And from all these set of states, you have still an option to add state 4 and state 6 by 1 step forward again. And then you have reached all the states, which in this case was from 1 to 6, which also equivalent can be described as x is not equal 0, which is, of course, in this case, a shorter description. And I mean, that's well known, that sometimes it's better to formulate a negation than a positive statement, because that can reduce the expression. Okay,
so,
some more?
Yeah, so this is more related to this finite automata stuff. Can we have more than one initial state in a finite automata?
Yes.
But then, according to the definition of the FA in, I think in most of the textbooks, they allow that unless a finite automata is modeled as a transition graph, we can have multiple final state. However, there could only be a single initial state in the FA design.
Yeah, okay. I mean, that's fine. In many textbooks, you have that. But my message is that, and definitely in many also computer science literature, there are the statement that you have a set of initial states. And there are some very interesting applications, for instance, in security. And generally, a non-deterministic system typically could have at least more than one initial state. But you have one point there, and that is that if you introduce what is called a silent event, an unobservable event, here we assume, or let's say that let's say that I would like to consider both 1 and 2 as initial states. I can also model that by saying that it's only the first state, and then instead of having an observable B, I consider that to be unobservable. It's something that don't give any sense of signal, and that means that I don't know if the system is in state 1 or 2 when it starts. And that means that you can also stay with only one initial state. But in that case, in the general case, when you have a non-deterministic automaton, then you have also these so-called epsilon transitions. So yes, there are different dialects of this. But and you could say that in the lecture notes I present, then typically I only assume one initial state, because then I get the deterministic system. And most of the methods I present in this course are actually based on the assumption that the system is deterministic. And then you only have one initial state. Yeah. But you're right that it's also typical that you have more than one goal state or marked state or final state or what you call it.
Thank you so much. And can you please summarize the meaning of the term predicate here, and in what sense are we using the term predicate, and how is this different from the preposition thing?
The reason why I am interested in introducing predicates here, for example, describing the reachable states, is that some algorithms are very much based on this type of predicate expressions. And also, of course, this is a way for me to illustrate how you can apply predicates on automata, because I mean the focus of my text or my applications here are automata, and instead of talking about fruits, apples and oranges, etc., to make illustrations of predicates, I use the state of automata instead.
Okay, thank you so much.
Great. Then backward reachability is also called co-reachability. And in that case, we are going backward from the marked states. And in this case, we only have one marked state. So now we formulate the predicate for the co-reachability predicate. Then we start from state 4, we go backward to state 3, backward to state 2, backward to state 1, and also backward to state 0. So here we see that all states from 1 to 4, they are co-reachable. They are backward reachable. So that means that what I call then PC of X, that where C means co-reachable. PC of X is then 0, X from 0 to 4. Or equivalent that X is not 5 and X is not equal 6. And then maybe you start to realize why I talk about these states as forbidden. Because if you look at this, and if you by mistake should take, if you should take the event E, or if some execute event E, then you reach into state 5, fine. Then you reach into state 6. But what is 6? It's a state from which it's impossible to reach the marked state. And also from state 5, it's impossible to reach the goal marked state 4. So actually, these are very bad states. They are also states which we call then blocking states. And state 6 is even a deadlock state. So these states are examples of states we would like to avoid. So actually, I've already presented here the first basic strategy for synthesis of a controller. Assume that you have this system given. And then I would like to ask for a controller which guarantees that I will be, in every state, will be able to reach a marked state. That is called a non-blocking controller. And the solution to that is to include state 1, 2, 3, and 4. Then I have the predicate representing the good states, generating the non-blocking controller. Let's see what it says on the next. It seems like when you jump back and forth or what it is, then it gets crazy. Let's see again. Yeah, okay. So here we had the predicate, here we had the automata, and now I can even define the forbidden state predicate, which is the combination of the reachable states and those that are not co-reachable and reachable. So here you have the reachable states, the predicate for that one, and the negation of the co-reachable ones. And the negation of 0 to 4 is 5 to 6. And if you take the AND of that together with 1 and 6, you get what? sorry, it's something wrong here. It's not equivalent here. It's the opposite, that these are. No, okay, sorry. Yes, we are defining now the forbidden states. Yes, sorry. So here are all reachable, and here are all that are not co-reachable, and then that generate the forbidden states. Yes, and those are the combination of 5, 6, and 1 to 6, and that generates 5 to 6. Yes, sorry, I was lost there. Then we could say that the acceptable state predicates, or the good states, they are PA here, defined as the reachable and the non-forbidden states. And then you get instead 1 to 4. So here you see that by introducing predicate calculus, I can actually formulate some algorithm generating the acceptable state predicate, or the model for, or a statement for the acceptable states, which are also the what I call the non-blocking states. So by having an algorithm that easily can generate these predicates, I can combine them in this way. And there are specific tools which are excellent to do that. And I've already mentioned that binary decision diagrams, BDDs, and also SAT solvers, satisfiability solvers, are the two most well-known examples of that. And binary decision diagrams came first, and you could say that there are some old famous papers where they say that, okay, we can, by these binary decision diagrams, make model checking or verification of systems for states of 10 to the power of 20 and above. I think that is the number they give there. And those algorithms are actually based on this type of technique. And there are, of course, specific solvers which make and tools which make these fully available. And I think I will mention that later on also in some sum up. But one specific tool is called new SMV. The first tool was called SMV. And then it was an extension called new XMV, and the last one is called new XMV. And in this new XMV, you can actually find the most recent good algorithm. And we try to compete with these algorithms. And actually, we have found that our tools at Chalmers sometimes really beat these algorithms which are considered to be absolutely on the top. But that is something I realized the latest month here. So we haven't written any papers on that. But I will present more about that later in the course. Then for predicate logic, we also have quantifiers as an additional topic, which is very useful. So then we can talk about, well, there exists at least one X for which you can do that and that. And then for all X, you can have a specific property. So when omega is finite, which we normally assume in this course and in the methods we are working with, then you can actually also define this existence of a predicate as an OR condition with including all elements in your in the domain of your variable or variables if you have more than one. So in this case, assume that omega has elements a1 to an. Then the statement there exists a p of x. There exists an x such that p of x is true. is equivalent to say that it's P of A1 or P of A2 or until P of AN. If that is true, then this existence X of P of X is also true. So you could consider this as actually a definition of this statement. Now you can realize that this does not work so well when omega includes infinite number of elements, but actually there are quite small changes in notations, meaning that it's still possible to work on that. But I consider that is not focus of this course. For all, of course, then we expect its replacement of or with and instead, because for all x, P of x must be satisfied. It means that it must be satisfied for AI, A1 and A2, etc. until AN. Based on this, we also get the number of predicate equivalences. For instance, that the negation of exist x, P of x, is equivalent to for all x, not P of x is true. And that can be easily proven by just replacing this negation of this existence formulations P of A1 or until P of AN. And then you apply the De Morgan's rule on this, and then you get not P of A1, and then you replace or with and, not P of A2 until and not P of AN. And this can then be considered as for all existence quantifier. So for all x, not P of x is true, is then equivalent to that there exists at least one x for which P of x, well, okay, there does not exist any, that is the meaning, there does not exist any x for which this is true, because if skip the negation first, skip the negation first, then it said, okay, the first statement here says that, okay, there exists at least one x for which P of x is true. But if you take the negation of that, it means that then it does not exist any x such that P of x is true. And that means that for all x, not P of x is true. Okay. This could even be considered as an axiom, if you like, and based on that, you can develop further rules. I will soon come back with some more examples, but let's see if I have something more to add. Yeah, okay, here comes a list of equivalences. So by some additional notations, I will prove at least some of these statements quite soon. And I consider this as I mean, we're talking about the tutorial here or showing more of examples. I consider this as an exercise. Actually, I think I should make a break here now and go for the other presentation to show you those things before I go on with the set theory. So let's.
Yes, you can. Please go ahead.
Yeah, okay. It's so quickly done, so I'm not sure if you need to stop the presentation.
Okay, fine. So I'll continue. Yeah.
Yes, you can do that. But of course, now I've become a bit stressed here. There, I think I have.
You take your time, Professor. We will. You can whenever you come back. We'll be here.
Yeah, but I think I am. Yes, something happened here in the end. Actually, can we take a 5 minutes break? So I have to because something happened just before I should compile and. So we take a 5 minutes break. Yeah, I think that's
sure. You please take it.
We will continue with 40 more minutes or at least 35 more minutes. Yeah.
Goyal, there is a WhatsApp group. We have sent invitations to all of them so that we can have a quick chat on some topic if you have. We have sent you also an invitation. You need to either you need to tell us. Either you need to tell us perhaps your WhatsApp number you have not added in the application form. So please add your WhatsApp number. If you can write here, I will add that. Okay. There are a couple of people whose WhatsApp numbers are not like either, whatever may be the reason, we did not have. Okay, thank you. I'll be adding the WhatsApp numbers.
So I think we can start then again.
Yeah, as you wish.
Yeah.
So if I'm going to start the recording. By mistake, instead of pausing, I stopped the recording.
Okay.
Yeah.
So can I start then?
Yes, please. Yeah.
Okay, good. So what I will do then is that I will just show you a couple of more examples on these small proofs of. First, this example was more or less what I showed you earlier. Actually this example, this version is a bit more extensive, which meant that I extended also this R conditional S to this replacement of conditional with an or conditional with the negation of the first one, and that gave me some extra lines here. But in the end, I got the same result, of course. So this is once again an example of a statement that is always true, tautology. Now I will show you also a few implications, actually 2 implications that were in the list of implications in the table. So it says that, okay, not P and P or Q implies Q. And okay, I mean, if you look at this, you could get the thing, yeah, it sounds reasonable, but let's prove that. So what we do then is that we take the negation of P and P. So, and then we have an or and not P and Q. So it's this multiplication addition rule. Well, I call it here. I don't know any well-known. You could, of course, you can call it an and or rule, maybe an and or rule. Yeah. Then we have here not P and P, which is then a contradiction. So then you have false or not P and Q. And that false or means that you can skip that and you only preserve not P and Q. And then we finally can use this implication that if an and statement means that both of them must be true, and especially Q must be true. So based on this, yeah, of course, and P must be true for this to, the negation of P must be true for this to be true. But it's not so obvious that implies Q. Yeah, okay. But this was one way to show this implication. But maybe you remember that I said that a contradiction can also be used to make a proof of this. So let's look at that one instead. And what we do then is that we take the first statement and implies the second statement, but then we put a contradiction on the second statement. So first, or say A implies B, then that is the same as A and not B. And in this case, A was not P and P or Q, and not the second, which was Q. This should generate a contradiction. Let's see. Yeah, okay. In this, you can take it in a different order. Yeah, okay. Now I see here. I kept that, and I have then not P and not Q. And here you can use this De Morgan, and you get negation of P or Q and P or Q. And this is, of course, something that can never be true. It's a contradiction. Then we can also simply look at this example where we have P and P conditional Q. And you could say that in most proofs, you replace P conditional Q with not P or Q. And if you do that, and then we use this and or rule, and then we have P and not P, or P and Q. Once again, P and not P is false. So here we get P and Q in the end, and that implies finally Q.
Excuse me, sir.
Yes.
I have one question, sir. When we are writing these implications, and for example, I11 or I12, on the left hand side we are writing some the logic, and on the right hand side equivalent logic we are writing, and then we are proving it to be as a contradiction. Okay, so if we want to we can say learn this in terms of the word statement, how will we express these proposition logics?
Okay, I'm not sure if I relate. Okay, let's first, if you talk about the contradiction version of this proof, that it comes here.
Normally, we prove them as a true proposition, not as a contradiction. So, is it specified that we need to prove it as a contradictory proposition logic?
No, I mean, let's repeat here that, I mean, an implication can be proved in two ways. Either you prove it as it is as an implication, and then somewhere you have to probably use a specific implication. For instance, that there are, if you have a combination where, if you have a conjunction, then both of these elements in the conjunction must be true. So that means that in this case, the second element in your conjunction must be true. And that is an implication. I mean, here in this case, it's not the opposite. I mean, Q does not imply that not P and Q is true, but going in the right direction, it's true. So that's so to say an implication. But then there is a well-known tradition that contradictions can also be used to prove implications. And I mean that you see a lot of contradiction proofs in any kind of mathematically oriented literature, and sometimes I have this word proved by contradiction is expressed a little bit sloppy. but here is the strict meaning of that. And that is that, okay, if you would like to show that P implies Q, say, then that can be proved by showing that P and not Q generates a contradiction. I think that's the only way I can express this.
Okay. Okay,
Yep.
sir. Okay. I think in the coming lectures we may find some example which will basically reflect the such type of propositions.
Yeah, okay. I see that now. I mean, you have a point there that, okay, these are only basic atomic propositions which I play around with. But the reason why I even introduce this is just that I would like to give some mathematical logic background to specifically motivate the set theory operations, because they are based on predicate logic. And I mean, in some of the, well, I would say for myself that I have had some use of these. Okay, I have had some use of these logical statements where I see more exactly how I formulate a contradiction proof. Because sometimes, okay, what proved by contradiction, but what does it exactly mean? It means exactly what I tried to state earlier. Okay, P implies Q, proved by contradiction, then you show that P and not Q is not true. It brings you into something that is not satisfied, but for this course it's not a big thing, and I will actually not come back to any contradiction proof anymore in the course. So this is more of a general background to mathematical background.
But I think there's sometimes in some problems we have certain constraints over the variables. Like we are assuming these predicates are basically the set of variables, and there are certain constraints for those variables, and the combination of those constraints does not come out to be true, although individually they are true.
And those could be examples where
those
this
can be such
contradiction can be used. Yes.
Yes. Thank you. Thank you, sir. Thank you, sir.
Yeah. Here, I just, as an overview, would like to show you that there is another technique which is some sense more general. It can also be used for infinite state systems or infinite domains, and that is natural deduction. But natural deduction has some details which are a bit more complicated. So for myself, I have the feeling that, well, okay, these simple equations and reasoning back and forth, which I show you, are equally good, so to say. But just to give you a flavor of what you see in many textbooks on propositional logic and predicate logic also, is that, okay, natural deduction is one very well known method. And then you could say that if you then have something you start with, and the idea is then that you should show that this implies something. And in this case, I should show that this statement implies S or Q in the end. Okay, that can be done in the way I show you down here. That, okay, first I have an implication 2, which probably means that P and Q implies Q. And then you get this expression. And let's see what we have here. Then, yes, okay, Q and Q implies R is another well-known implication. So Q and Q implies R gives you R, and then you only have R and S or not R for the rest here. And then not R or S can also be expressed as R conditional S. And then once again, R and R conditional S means S. And if you have a statement is true, then you can always add a conjunction to that with anything, for instance, like Q in this case. So this was the way I would say I prefer normally to work on this kind of expressions. But here you can also use this natural deduction, and then you take parts of your expression up here as premises. For instance, P and Q conditional R, and later on you will have S or not R as the third premise. Then you take the implication 2 and apply that on the first premise, and then you get P and Q implies Q, and then we combine I12 on 3 and 2, Q and R and Q, that means R, and
so
then we
perhaps
yes?
your slide, if I'm not wrong, if slides are the same slide is there, there's no transition of slide. It is showing to us P and P implies Q and not Q. This is like, yeah. This is slide number 65.
The problem is that I don't have any slide numbers, but let me see if I make a switch now. Can you see now that I have implication I11 follows by contradiction?
Okay.
And now I go back to this. I should have added a natural deduction headline up here, but now I was down to this premise S or not R, statement 5. Can you see that now?
No, there's no transition of slides, Professor.
Okay, so let me ask again then. If I show you here predicate logic quantifiers, don't you see that?
No. No, sir. In fact, you made, can you please do can have a new share and then?
Yeah, exactly. I do that.
Okay.
It's amazing that that it's not stable enough on this. Can you see now predicate logic quantifiers?
Yes.
Okay. Sorry. Now I try to go back. Can you now see this?
Yeah, now we can see that. Yeah.
Okay. So yes. Then I need to say more clearly when I switch the slide, and if you don't see that, please tell me immediately. Yeah. Okay, so I was on this fifth line of this premise S or not R, and based on that you can also write that based on the equivalence E20 as R implies S. And if you combine that with R, you get S. And once again, including the third implication, you get S or Q. Okay, this is not a big deal. I just show you how you can use natural deduction also to work in the same way as I have done here. Actually, the way I use here with these list of equivalences back and forth, it's not very common in the literature. I'm a bit surprised on that, but that's the fact. They more talk about natural deduction. Okay, then now you see, I hope, the contradiction aspect, implication I11 follows by contradiction. Do you see that?
Yes, sir.
Yes, Professor. Yeah.
Okay. I've already mentioned that part, and I will give also the second implication here, the I12. So that means that I want to show that P and P conditional Q implies Q. And then I formulate that instead as a contradiction, and I take the and not Q instead. And then I should show that that generates a contradiction. And it's quite simple. I combine P and not Q, actually then you can use De Morgan on this, and you get not P or Q, and that combined with not P or Q generates a contradiction again. The same expression with an and the negation before one of them is something that can never be true, and it's a contradiction.
I have an observation here.
Yeah.
So I have an observation here that here we have three premises, P, and then P implies Q, and then negation of Q. So we could have take the help of the modus ponens over the first two premises, say P and the P implies Q, resulting into the value Q. And then Q and the negation of Q will obviously lead to the contradiction. So
I'm sure. I'm totally right. I mean, there are different ways to present this, and so that means I could actually have written these equations in another way. Yes, that's right. That's right. You are right. Thank you. Actually, these parts I think I've already discussed on this, because I said that the existence can be expressed as or condition, but now I introduce a specific notation on this or on a set of elements, just to avoid to write this all the time. So that means that actually the existence of P of X can be described as this set of or operators on P of A, where all A belongs to omega, and the for all means that you replace the set or with set and instead. Well, here's some bad handling in LaTeX when I compile it, but we can skip this, and then I will just show you at least two examples here. Actually, this was what I showed you, but here in a shorter, more compact way, that the negation of existence P is the same as for all X not P. But the second one, let's take a look at that. What this says is that it's actually an interesting implication here, which is if you should show this by this kind of expressions here, it would be a bit complicated notation wise, not from a logical point of view, but here is a quite short version of this. What I do here now, I say that when I express there exists P of X and Q of X, that can also be expressed as P of X and Q of X is true for one specific element, A in omega. And this is a trick which is also used in natural deduction. And then based on that, you have an implication, namely that, well, if something is true just for one element, it can be true for a lot of other elements, actually for all elements in omega. Now here it's just true for one element, but that implies that this set or here are also true. Meaning, once again, that if something is true for one element, it's true for the or of all elements. Observe, this is an implication. The opposite, of course, is not true. Then this for all, not for all, but the or condition of P of B, that can be expressed then there exists P of X, and then there exists Q of X. So this short derivation here with this trick that the existence can be described in this way means that we have actually showed an implication that there exists P of X and Q of X, implies that you can take the existence operator on the individual element, but the opposite is not true. So if you have this condition, this does not imply this.
So will it leave any impact if I go for the quantification of, if I use different variables in the quantification, like say instead of using there exists X, what if I could have this could have been like, say, there exists X and then there exists Y, P of X and Q of Y.
Aha, okay, if you would like to have a mix of variables.
Yes.
Yeah, so then you should have an existence of X and Y here on the outside part.
Yes.
And that could have meant that, yeah, I think that would work fine too. But I think I would like to evaluate it in some more detail before I say that 100%. But it sounds like you are right there, yes?
Right. Thank you.
So then I would like to get back to the other presentation to say some more words about set theory before we stop. So I start the presentation again from the other. Yes, there we have it. And when I mention about this, I will also say that my presentation, I will send that by an email, so you can take a look at that if you like afterwards too. Let's see if there are some more chat. Okay, I don't think it was anything specific for me. Let's go on and see if we have this. Yeah. So then finally, some words about set theory. And that is, on the other hand, a very central part in the course, because we will work with a lot of set definitions later on. So first we say that, well, a set just includes a number of elements. Actually, we had a set omega where we had the domain of the variables. Now I talk about any type of set here, just including a couple of elements. And then, of course, I can write IE belongs to A, but BI does not belong to A, because BI is not an element up here. So, for instance, in our automaton, which we will define tomorrow, then I will introduce the notation that I have a set of states in my automaton, and then the elements can be denoted Q1, Q2 until Qn. That's a standard notation. In the examples I've given so far, I've called the states integer numbers. So it was 0, 1, 2, etc. But it's also quite common to have these more symbolic notations. Then we can also actually define a set by a predicate. So if I say that set is all x such that x is a natural number, actually I could have written that in the beginning here, and that x is less or equal 5, that is this set, elements from 0 to 5, and now I assume that the natural numbers include the number 0. So that's quite powerful to define sets that you use predicates. And that means that generally a set A can be defined as all x such that a specific predicate P of x is true. That also means that I can define, for instance, some basic operators on sets like union, intersection, set minus, and the complement of A. And here my predicates, remember that this is a predicate. AI belongs to A is a predicate. That can be true or false. So in this case, X union B means that X is a member of A or X is a member of B, then it's a member of the union. While the intersection means that X is both a member of A and B, while set minus means that it's a member of A, but not of B. So any element in B is removed from the set A. And the complement of A is then all elements that are not a part of A. So it's, so to say, you could say it's negation or the opposite of the set A. Another interesting aspect of sets is that they are unordered and you don't include repeated elements. So for instance, the meaning of A1, A2, A2 is the same as A1, A2. You normally don't repeat. I mean, if you write A2, A2 in a set, it does not give you anything extra. It's just that A2 is included. We will later see another type of sets called tuples, where this is very central. That's an ordered set, we can say, but ordinary sets are unordered. And that also means that the order doesn't matter. So A1, A2 is the same as A2, A1, which could sometimes be a bit frustrating, but that's just the definition. So here we can then apply these rules on, for instance, a set A with 1, 2, 3 and B with 2, 3, 4. And we make the assumption that the whole set is from 0 to 5. So that means that the union of A...
There's no change in the slide, sir. There's no change in the slide.
You don't see the slide?
No, we cannot. This is a PDF document. Please go to the slideshow.
Okay, so I go back again. Good. Good. Now you can see?
Yes, sir.
Yeah, good. So A is equal 1 to 3 and B equal 2, 3, 4. And the definition, the domain from 0 to 5 means that A union B includes both A to 3 and 4, while the intersection is only the shared 2, 3 from both. A set minus B, B includes 2, 3, 4, and specifically 2, 3, and that is only one back, which is unique for A compared to B. And the complement of A, since we have the domain from 0 to 5, is then A does not include 0 and 4 and 5. So that's the complement. Now there is an interesting relation between set algebra and predicate logic, in the sense that set algebra, if that includes union, intersection, the complement, those corresponds to the predicate logics or, and negation. And the whole set corresponds to true in predicate logic. The empty set corresponds to false. While the subset operator, which I haven't defined, but okay, I guess you are familiar with that, of course, that corresponds to the implication, and equal corresponds to equivalence. So then we have some special sets that A is a subset of B, and that could be defined as all X such as if X belongs to A, it also belongs to B. And this is always, this is a tautology. So if you like, you could also have written this as for all X belongs to A implies a double arrow here. Equal set means that they are subsets of each other. So A equal B means that A is a subset of B and B is a subset of A. The power set is all X such that you have a contradiction, P of X and not P of X generates the empty set. While the universal set includes all sets, and there you have the tautology here instead. And that's also the reason why we say that the universal set corresponds to tautology, the negation corresponds to contradiction, And here you see these relations. Do you see power set now?
Yes, yes.
Great. The power set of all is actually the set of all possible subset of a set. And sometimes that's quite useful, especially when we work with some non-deterministic descriptions, which will be more clear, hopefully already tomorrow. And that could be written as 2 to the power of A or a POW of A or something, but it's called the power set. And that is also actually all sets such that the set X is a subset of A, which is, of course, includes the A itself, because A is a subset of A. It also includes the empty set, because the empty set is also a subset of A. So the power set, when A includes 1, 2, 3, includes these empty set, the set with 1, only 2, only 3, and 1, 2, 2, 3, 1, 3, and the whole set A. So all subsets of A is the power set. Then we also have this proper subsets. A is, so to say, proper subset of B means that A is a subset of B, but A is not equal B. So in this case, A is absolutely smaller than B. The number of elements in A is absolutely smaller than the number of elements in B. So that could be actually another way to define a proper subset, that the number of elements, the cardinality as it is also called sometimes. And then the cardinality is written, or the number of elements is written as a vertical line before and after the set. That tells, okay, the number of elements in a set. Well, now I would like to make a proof here, which I've looked in so many textbooks to see a correspondence to this, because I'm sometimes a bit uncertain how I use the notations and so on. But I have never found that in any textbook, but I find that quite interesting and definitely useful. Yeah. So that means that I would like to show the implication. A is a subset of B implies that A intersected with C is a subset of B intersected with C. Sounds quite reasonable, because A is smaller than B, or at least it could be smaller. But let's prove that. Well, what we do then is that this A subset of B, that I formulate now as using this expression. I don't include the tautology notation all the time. I think that formally one should do that. In some literature, they skip that tautology description. So yeah. Okay, let's go for this. The important that I cannot write implication here. I must use the conditional statement, because I would like to go further and to replace this with not X belongs to A and X belongs to B, etc. But that comes on the coming lines here. So I say that A is subset of B is equivalent to this expression. And it's actually equivalent to, I missed the equivalence there, I see. Oh, no, sorry. No. Okay. A is a subset of B is equivalent to this expression. And now I go instead for this and look at what is A intersected with C. It's that for all X is a element of A and C. And here I use the subset and replace that with the conditional statement. And B intersected with C is B and C with X before. So this can now, here I have a conditional statement, which I can then replace with or and the negation before this. So this is equivalent to not the first statement or the second statement. And then I take the De Morgan here, and that means that I have now X does not belong to A, or X does not belong to C, or, and what is coming after that. So then I can also rephrase this as these three OR conditions and the corresponding X not A or X not C or X belongs to C and an and in between. So I have used this, I call it sometimes the combination of or and here. So now we see here that here I have X not equal C or X is in C, X not in C or X in C. This is a tautology. And a tautology or something else is also tautology. So, and then you have a tautology and that means that I can skip this whole part. So now I only have X not in A or X in B or X not in C. But I had an implication up here. I said that, okay, if this is true, then this is true also. So now I can use this fact that X A implies X B is actually something I can use that is true. And since this is true and this is equivalent to this expression, and that is a tautology since A is a subset of B. Then, since I have tautology or something else, I know that all this is true. So for all X, I have shown a tautology, and that means that we have shown this expression up here. Okay. Not too complicated, but you have to be a little bit careful. And by this, we have used predicate logic to show set expressions. Now, there is also a table of set expressions, which is very similar to the equivalence table for the propositional logic parts. And you can really see the equivalence, the correspondence between this. Say, for instance, that A union the whole set is the whole set. That corresponds to P or tautology is equivalent to tautology. And you can go through this list and see a lot of correspondence. Actually, many of these set expressions can be proved by just applying this set table. But the interesting is that there is not much of subset expressions here. Well, actually, I have something in the end here. But as soon as you have these subset expressions, it's more of interest to also apply predicate logic. So then I don't have many more slides. I think it's actually only 2 slides. Just a quick summary of what is also called ordered sets or tuples. In that case, if I write A1, A2, and A3, the order matters. So that is not equivalent to A1, A3, and A2. And these angle parentheses could be replaced by ordinary parentheses, if you like, both of them. Yeah, also ordinary parentheses can be used, as you see here. Here comes now the important aspect of cross product. And the cross product is actually something we are very much need. We very much need when we should define the synchronous composition. Maybe you remember this morning I mentioned about a model for the closed loop system, and then I wrote P synchronized C or G1 synchronized G2 I gave an example on. And then we really know, really need the cross product. And you could say that the cross product of two sets is just a combination of all possible combinations of elements. So if you have a set X and a set Y, X cross Y includes X1 and combined with all the Y elements A1 to Y1 to Ym, and X2 with all Y elements until Xn with all Y elements. You could say that this corresponds quite much to a vector. How is it now? Isn't it a vector multiplication where you have first a column vector multiplied by a row vector, then you get all these combinations. So you could also say that X cross Y is all combinations XY, such as X is an element of X, small x is an element of capital X, and Y is an element of capital Y. So that means actually that the order here doesn't matter, because this is a set element, but in itself it's a tuple or an ordered set. So remember that the whole thing here, the cross product, is a set where you can take any order of the elements, but the individual elements are in itself, are they tuples or ordered sets. So for a synchronous composition of G1 and G2, if the first automaton has a state set Q1 and the second one has a state Q2, actually the set of states in the synchronous composition is exactly the cross product between these two sets. And then there are some special rules for these cross products, but I think I skipped them. Just it's important that you take the right order here. So generally A cross B is not equal to B cross A.
So sir, what this synchronous composition is, what does it mean?
I tried to exemplify what I mean by the synchronous composition this morning, but tomorrow I will define it formally. Okay. So I just say now that in the definition of the cross product, in the definition of the synchronous composition, we will need this cross product. So that's one reason why I introduced this cross product as an important part.
All right. Yeah.
Great. Final slide. I should also mention some things, some elements of graph theory and search algorithm. First, we can say that automata, they are really graphs. Sometimes it's even so that the automaton is more of a tuple of mathematical sets, expressions. And then some people say that, okay, then this graphical descriptions is just a graphical description of the automaton. But for me, I use, when I say that I have an automaton, I expect that I see something like this graphical description. So for me, it's a synonymous thing. Now I have two automata. Both, this is just an example I had in my presentation, so I brought that up just to illustrate also a little bit more on this search algorithm. But before I illustrate the search algorithm, I should also mention that this automaton is a directed graph. it means that the edges, which they are called generally, they are arrows. So there is a clear direction from 1 to 2. Forward transition, a forward transition is from 1 to 2. And then the circles here, they are either called nodes or states, and also in the graph theory, they are often called vertices. But for me, I will only have, we can say, automata and a little bit, very little on Petri nets. And then I'm talking about states and transitions. And the states are nodes, and the transitions, they are these edges, directed edges. Now, when you synchronize these two, actually, I said already here that we should take the synchronous product of all the states of the individual states. That means that we get one combination 1, 1, 2, 1, 3, 1, etc. And they come here on the first column. On the second column, you combine the second state of the second automaton with all states in the first automaton. So altogether, this illustrates nicely the fact that the synchronous composition is actually the state space is the cross product. But the last thing I would like to mention is about this search algorithm. And this, what I talk about now is the breadth first search, which is the most common one. And then we are thinking about the reachability analysis. So what we do then, we start in the initial state, and this is now only a unique state. Then I go for one step forward, and one step forward, it means that I get here state 1, 2, and here's state 2, 1. So after one iteration, I've included 3 states. And based on these 3 states, I can take one more step forward, and then I will get this 1, 3 state, the 2, 2 state, and also the 2, 3 states. So now I have 3 plus 3 states. I have 6 states. And then you go on like this, take one step forward, and in all directions. And in that way, you obtain what we call breadth first search. And in this case, how many iterations do we need to capture all the states? Actually, I think we need 2n-2 iterations to reach all the states with this breadth first search. Once again, breadth first search is the common tool for generating reachability, the reachable states. But when we think here about 1 billion states, then it's not so easy. And if we talk about 10 to the power of 100 states, it's totally impossible. So then we need smarter tricks. But what we try to do then is either to include smart data representations of your states like BDDs, or you have smart Boolean operations like the satisfiability solvers, or finally to make abstractions of our systems. And in this case, if we are just interested to ask the question, is it possible for the synchronous composition to reach a goal state in the combined system? And then by abstraction, I can obtain a 2-state model. The first state represents all the non-marked or all the non-goal state, and the final state, the second state, represent this state. And using that abstraction with the 2-state model, I can of course see that yes, my goal state is reachable. I will come back to that later, but that's a very powerful tool. Sorry that I took too much time, 1/4 extra, but by that we are ready tomorrow to go on with the automata definition and formal language. So thank you, everyone. Let's see if we have one more question here.
Yeah, so there are a couple of questions, Professor. Thank you so very much.
Yeah.
There are two questions in the chat. Request Deepojwal and Neeraj, will you please ask questions if you have? No?
So just wanted to ask if discrete event system modeling can be modified to include real-time new events if certain unknown, unobservable event occurs. These are excellent comments. Yes, real-time models, definitely. And then we talk about timed automata. Actually, in parallel with this course, I am trying to write a paper on timed systems and also including optimization to that. So maybe next week, when I must have finished that paper, because on Tuesday night next week, I must finish that paper. And after that, maybe I can tell you a little bit about that. If certain unknown observable event occurs, actually, I don't understand the final comment there. Can you express yourself a little bit more on that?
Hello, sir.
Yeah.
So I was asking if some model is already made.
Your voice, your
Sorry,
voice is
sorry,
breaking, Deepojwal. Your voice is breaking.
Hello.
Deepojwal, your voice is breaking. Can you write? Can you please elaborate on the chat box? Your voice is breaking.
Is there anyone?
In the meanwhile, if there's any other question, or I request all of you to please start your videos as it is mandatory from GIAN side that we should all be recording all the attendees. So may I request all of you to please.
Yeah, okay.
So please put on your
okay,
videos.
So I should stop sharing then, yes, okay.
Yeah, yeah, thank you so much, all of you. And please feel free in asking questions, as I said before. Yeah. So now you can, so Deepojwal has written, he has written,
one question.
Deepojwal has written his, in the chat box, if a system is already modeled, how can I incorporate some new events in that model in real time?
Aha, okay, now I see. Yeah, okay, that's interesting. Well, I would say that it's not, so to say, a general technique. What I think about then is actually learning principles. So you could say that if you try to, for instance, learn a state machine, which is perfectly possible, of course, then you can say that is a real-time possibility to extend your model. But if you should make an analysis on a model which is, so to say, always changing, of course, you cannot say anything about what will happen in the future, which you haven't given to the algorithm. So if you are asking, for instance, for the reachable states, if you go in one direction, maybe one specific state is not reachable, but then later on you will reach some other states and you add additional transitions, and then suddenly one specific state, say goal state, is reachable. So those kind of things, you must have the complete model to really be sure that all properties can be analyzed. But you can definitely add more events by a learning procedure. Yes. Good question.
So we can take one last questions because somebody was asking that can. May I know who was asking a question?
Aha, can we correlate this theory with fuzzy logic? Hmm?
Yeah.
Yes, yes, sir.
Hmm?
So, could you
I would
please
s-
answer that, sir?
Yeah, I would say that the connection to fuzzy logic is quite small, actually, because here it's a logic system more, and then it's 1 and 0. Fuzzy logic, I would say, is more a suitable tool to describe things that have still a continuous behavior, where you can go smoothly from one state to another, or that there, yeah. So I would say that fuzzy systems are more suitable for relation to, say, feedback control systems and so on.
Thank you very much, sir.
Yeah.
Thank you, Professor. And may I once again request all of you to please open your cameras so that we can record your presence. Thank you. So day 1 is excellent. We request all of you to please join tomorrow before 3 p.m. so that we can start at time sharp at 3 p.m. On behalf of IIIT DM Jabalpur and both the coordinators, we sincerely thank you, Professor. It was such a good learning experience for all of us. I hope all of you have enjoyed. And may I request Shubhangi to please take the print screen and save it. Thank you. Thanks all. Enjoy your dinner with your family and friends. We are meeting tomorrow at 3 p.m. And for Professor Bengt, it is still the day. I think he is half the day available with him. So
yeah,
Professor.
I will continue with my paper.
Yes. Thank you so very much.
I see here there was one more question. Is there any lab simulation topic available? Well, yeah, there is. We have one tool called Supremica, and you can download that. It's I will yeah, I can even write that, Supremica. If you search on the web, you can definitely find a pointer to that, and by that you can play around a little bit with automata and so on. And there are a lot of small examples and also big examples. So when I said that we have some algorithms that it looks like they are able to compete with the absolutely best algorithm in the world, it's based on the implementation in the Supremica. Then I would also recommend this tool, New XMV, which you can also search for. There you have a lot of verification tools. It's not so much of, yeah, okay, yeah, you can say there is a bit of simulation environment in that too. There are, of course, other tools also available if you look for model checking and so on.
Can you write on the chat box to everyone the spelling so that we can?
Yeah, I wrote in the chat box. Okay. Yes.
But to whom? I don't know. It's maybe I have missed that. I'm sorry.
I wrote. I mean, I can see at least Supremica and New XMV 15. Okay, it's not relevant. Can the rest of you see Supremica and New XMV?
No, not visible.
You have written to some specific participant, perhaps. Yeah.
Aha!
Yes,
Okay.
Yes, I have typed
Yeah. Sorry. Yes, sorry. Okay. Sorry. Yes. Where do we have everyone here? Everyone in meeting. Yes. I'm an amateur on this. Okay. To everyone. Now I write Supremica. and I also write new XMV. Now, sorry, I spelled Supremica wrong. I have to write it again. Supremica and new XMV. Now it should be correct. And I hope you see it, everyone.
Yeah, we can see that. Thank you so
Yeah.
much.
Okay, good.
Those who are interested can download that.
Yeah.
And a very good night to all of you, and a very good day, Professor. We are meeting tomorrow.
Yes, yes. See you then. Bye-bye.
Bye-bye all.
Bye.